This is Chapter 8, Inferences for a Population Mean. So here's a motivating example for us. Nationally, the average score on the ACT test was 21.1 in 2009. The population standard deviation was 5.1. Suppose researchers in Utah are interested in evaluating how their state is doing preparing students for the ACT. They would want to know if the Utah average was different from the national average. So what is the population the researchers are interested in? Well, these researchers, to me, it sounds like they are only interested in all the students in Utah. And what could be their parameter of interest? Well, they're interested in comparing their mean to the national mean, so we could do the mean of all students in Utah. Now, statistical inference is the science of deducing properties of an underlying probability distribution from a sample. Or we could rephrase that as trying to figure out properties of a population from a sample. There are two main aspects of inference. The first one is estimation. So that allows us to address questions such as, well, what was the average ACT score of Utah students in 2009? We've already done a little bit of this with our point estimates. Then hypothesis testing enables us to assess whether the average score in Utah was different from the national average. So in estimation, we say, okay, what is our best guess for what the score is in Utah? And hypothesis testing we can say, well, someone thinks it's 22, we can test to see whether or not they are correct. So the first part, estimation, we've learned how to do point estimates. Now we're going to do confidence intervals. So if we have confidence intervals for a mean, the notation for population versus sample. I just threw this in again so you can look at it, review it, make sure you have this memorized. Okay, remember our sample mean x bar is an estimate of our population mean sigma. We call it a point estimate because the sample mean is just one number or a single point. Now that doesn't give us a lot of data, it only gives us 1 point. We can try and use a little bit more data. We can give a more meaningful estimate. And the way that we do this is with a confidence interval. So a confidence interval for our population mean is an interval constructed around the sample mean so that we are very sure or confident that this interval contains the population mean. So for example, when we want to estimate the mean ACT score of all the students in Utah in 2009, we decide to take a sample of 50 students and find a sample mean. Assume the scores are normally distributed. So our sample mean is our point estimate of the unknown population mean mu. But remember, our samples, we have many samples to choose from, and for every sample, we could get a different sample mean. So unless we're extremely lucky, our sample mean is probably not going to be equal to our population mean, but it should be close. So let's start with a little theory. Remember, what is the sampling distribution of x bar? Because we assume that our scores are normally distributed, okay, then our sampling distribution will also be normal. And our mean for x bar should be equal to the mean of the original population. We don't know what that is. And the standard deviation for x bar should be equal to the original population standard deviation divided by the square root of n. So start off, what does the empirical rule tell us about x? Okay, do you remember the empirical rule? Okay. We start with anything that's normally distributed, such as our x bar. It's going to be centered at the mean mu. Okay. And then we learned that if we go out plus or minus 1 standard deviation to either side, that there should be 68% of the observations there. So we know that 68% of all the possible values the empirical rule tells us about 68%. So about 68% of all the possible values of X bar fall within mu plus or minus sigma X bar. And then, so 68% fall within plus or minus 1 standard deviation, about 95% fall within plus or minus 2 standard deviations, and about 99% of all the possible values of X bar are going to fall within the mean plus or minus 3 standard deviations of X bar. Now that about 95%, that's an about because, well, first of all, it's dealing with real data, and real data usually doesn't follow our distributions exactly. But secondly, because if you actually look at the standard normal table and you try and figure out what z-values have 0.95 in the middle. So let's go, if we have 0.95 in the middle, then that means we have 0.025 in each tail. So let's go to our normal table and look for 0.025 in the tail. And it looks like my z-value is negative 1.96. So this is negative 1.96 and this is 1.96. Okay, so it turns out that if you want to actually get your 95% of your observations, that it's 95% of all the possible X bar values fall within plus or minus 1.96 standard deviations of the population mean mu. Okay. So we're going to use the number 1.96 just because it's slightly more accurate than our 2. Now let's think about that. So if X bar is supposed to fall within plus or minus 1.96 standard deviations of mu, then that would mean that mu has to be within plus or minus 1.96 standard deviations for X bar of X bar. Now, why would we want to rephrase it like that? Okay, it's because the second method is much more useful to us because usually we know X bar, but we don't know our population mean mu. So if we want to estimate with our X bar, then we're going to be pretty sure that mu is going to be within plus or minus 1.96 standard deviations of X bar. Okay. So, one more time, a 95% probability that the sample mean X bar will be such that the interval X bar plus or minus 1.96 sigma X bar contains the population mean mu. Now, where does that probability come from? The probability comes from which X bar value did you get? Did you get an X bar value that was within your 2 standard deviations? Because if you did, then mu is within 2 standard deviations of X bar. But you might have gotten one of those 5% of the X bar values that is far out in the tail. So it is more than 2 standard deviations, or more than 1.96 standard deviations away from my population mean mu. And so my interval isn't actually going to contain mu. So what happens is before we randomly select our sample, there's a 95% probability that we will obtain an interval X bar plus or minus 1.96 sigma X bar that contains the population mean mu. So in other words, 95% of all the intervals we might obtain if we took many, many samples contain our mean mu, and then 5% of these intervals do not contain our population mean mu. So this is why we call our interval X bar plus or minus 1.96 sigma of X bar a 95% confidence interval for mu. Let's see how we actually use this. So we now take a sample of 50 students, so n equals 50, find a sample mean of 20.3, and assume the population standard deviation is 5.1. So we want to find a 95% confidence interval for our population mean ACT score. So we want to use the formula X bar plus or minus 1.96 sigma over the square root of n, and just plug everything in. So we have 20.3 plus or minus 1.96 times 5.1 over the square root of 50, which is 20.3 plus or minus 1.41, which gives me 18.89 to 21.71. So this is my 95% confidence interval. So I am 95% confident that my population mean ACT score, or the mean ACT score for all the students in Utah, I'm 95% confident that it's between 18.8 and 21.7. Notice that tells me a little bit more information than just the fact that my sample mean was 20.3. Now, because we don't know the true value of our mean mu, we don't know for sure whether mu is contained in our interval. But we are 95% confident the mu is in the interval. So we don't know for sure, because again, we could have gotten one of those really extreme x-bar values, but we're 95% confident. And when we say that, what we mean is that we hope that the interval, which we got is 18.89 to 21.71, is one of the 95% of all intervals that contain mu, and not one of the 5% of all the intervals that don't contain mu. We say that 95% is the confidence level associated with our confidence interval. This confidence level is a percentage that intuitively expresses how confident we are that the confidence interval contains the population mean. So in our situation, we would say that we're 95% confident that the population mean ACT score of all the students in Utah is between 18.89 and 21.71. Then I might ask you questions such as, do you think it's plausible that the mean Utah ACT score is 5.1? So, let's cross that out. We wanted to go 21.1. That was the national average. So do you think it's plausible that the mean Utah ACT score is 21. So I would think that it's plausible that our mean Utah ACT score could be 21.1 because 21.1 is included in our confidence interval. So because 21.1 is in that confidence interval, I think that's a very plausible value for our mean ACT score. So to really understand the meaning of a confidence level, let's go ahead and look at an applet. So for this applet, you'll notice that we start off with a normal distribution, okay, the center and the mean mu. You may not realize this, but this is the normal distribution for our sample means x bar, okay. And so what happens is we take one sample. Notice this little red line. You might not be able to see it very well, but there's this little red line in the center. That was the sample mean for that one sample. And then they found a 95% confidence interval. Okay. And notice that this 95% confidence interval did contain my population mean mu. I can take another sample. Notice that my sample mean changed, but my confidence interval still contains my population mean mu. Another sample, yet again a different sample mean, but my interval still contains my population mean mu. Okay, a different sample mean, a different sample mean. Let's try a few of these. Okay. Notice on each one that my sample mean, the little red bar, changes from sample to sample, but most of these confidence intervals still contain my population mean mu. Oh, look at this red one right here. Notice my sample mean was so far off to the side that my confidence interval doesn't actually overlap with my population mean mu. Okay, let's try and do 50 a few times. So we're up to 491. Sorry, we've done a total of 519 confidence intervals. And of those 519 confidence intervals, 95% of them actually contained my population mean mu. That is why it's called a 95% confidence interval. If I switch these to, say, an 80%, okay, notice that they got a lot narrower and a lot more of them don't contain my population mean mu. Okay, and in fact, if I take lots and lots of them, I'm around 82% that actually contained my population mean mu. And if I did it many, many times, eventually I will get to where 80% of my confidence intervals contain my population mean mu. So that's the definition or the reasoning behind a confidence level. So I drew a picture in here just so you can remember in the future. Okay. And now we're going to talk about the general form for confidence intervals. So every confidence interval you ever come across is written in the form of an estimate plus or minus a critical point times the standard deviation of the estimate. Okay. Now, if you ever have to estimate the standard deviation of the estimate, then it's just your estimate plus or minus critical point times the standard error of your estimate. So in our situation, our estimate for our population of mu is x bar. Our critical point we'll leave for later. Okay, and standard deviation of x bar is sigma over the square root of n. So let's look at our actual formula. So our one sample z confidence interval. So this is what you use if you know the population standard deviation. So 1 minus alpha confidence interval for mu is x bar plus or minus z alpha over 2, sigma over the square root of n. So this z alpha over 2, notice it is the critical point in my formula. Or I can write it as x bar minus z alpha over 2, sigma over the square root of n, and x bar plus z alpha over 2, sigma over the square root of n. Now z alpha over 2 is your critical point. The notation is they're trying to help you figure out what you need to do. I say forget all the notation and just draw a picture, and it will work every time. Okay. Before we draw the picture though, you need to know that this interval is exact when our population distribution is normal, and approximately correct if the sample size is large, at least 30 for any population. Okay. So how do you actually find a critical point? So again, the easiest thing to do is completely ignore all of the notation. Okay, and let's say you want a 95% confidence interval. Well, you say that means I need 0.95 to go in the middle. And if I need 0.95 to go in the middle, then I have 1 minus 0.95 or 0.05 left for each tail. So in this situation, alpha equals 0.05. Okay. And that's how much is left to go in each tail. So if I do alpha divided by 2, then I have 0.025 for each tail. Okay. Notice again, just ignoring the notation completely, and just draw a picture. Okay. And now I need to find my z values that will make this happen. So if I go to my z table again, look at 0.025, I find that my z value is negative 1.96. So technically, z for alpha over 2, or z of 0.025, is 1.96. Now m is our margin of error, and it's just defined as the part that you add or subtract in your equation. So in this case, critical point times standard deviation over the square root of n. And that is our margin of error for when we want to estimate mu by x bar. 1 minus alpha is called the confidence level, so that's usually our 95%, 99%, etc. Notice we can also write this formula, x bar plus or minus z alpha over 2, sigma over the square root of n, as x bar plus or minus z alpha over 2 times the standard deviation of x bar. And that makes it fit with our general formula. So here's an example. An automaker has introduced the new midsize car and wishes to estimate the mean gas mileage mu for all the cars of this type. Assume that sigma equals 0.8. They took a sample of 50 cars. So let's write down everything they tell me. Okay. N equals 50. And the sample mean is x bar equals 31.56. Find the margin of error for a 95% confidence interval. First thing you need to do is check, did I start with a normal population or a sample size of at least 30? So that it's okay to go ahead and use this procedure. And we do have a sample size of at least 30, so we can use our procedure. So I need to find my critical point, which again, I'm just going to draw a picture. Okay, 0.95, so that's 0.025 in each tail. So this is 1.96, so my critical point is 1.96. So my margin of error is z alpha over 2 times sigma over the square root of n. So 1.96 times 0.8 over the square root of 50, which gives me 0.2217. Now let's say you want to find and interpret the 95% confidence interval. Remember the formula for this is x bar plus or minus my critical point times the standard deviation over the square root of n. We've already figured out what this portion is. We just need our x bar, so 31.56 plus or minus 0.2217, which gives me 31.33 to 31.78. And what this tells us is that we are 95% confident that the population mean is between 31.33 and 31.78. We don't know for sure, but we're 95% confident that our population mean for all the cars of this type is between 31.33 and 31.78. And so finally, they will get a government tax credit if the population mean gas mileage is at least 31. Do you think it is plausible that the mean mileage for all the cars is at least 31? Okay, so why or why not? Okay. Well, if you look at our confidence interval, all the numbers in our confidence interval are at least 31. So I'd be 95% confident, at least, that my mean gas mileage is at least 31.